The NAND circuit forms the basis for all logic circuits. The reason is that you can build all logic circuits exclusively with NANDs. This also works with NOR circuits, but I will use NANDs as a basis here. This is the truth table for the NAND. As you can see, a 0 is only generated if both inputs are 1, otherwise a 0 is generated. Then let's program this. First, create a new class as the base class for all integrated circuits. We import and set the base class to component. We not only pass the object to the constructor, but also a list of all ports. We pass the object, calculate the number of ports and create a list from it. Now we create a dictionary which contains the ports as keys and the number as a value. Now let's initialize some attributes. And calculate the minimum and maximum of the ports. We will create the findPort method later in the component class. We write about the checkEndPoint method. Here vec is the vertice of the wire. We are looking for the port in whose range the endpoint is located. We save this. The next call after add connection will use this. The setInputState method goes through all connections and tests whether this is an input and with. Connected to one of the ports. If yes, we change the status of the port and calculate the result. Finally, we create the prototype of this method. Now let's customize the NAND class. First we change the import from component to IC. We customize the base class. The names of the ports are added to the constructor. We now write the setState method. Here we call the setInputState method of the base class. Now let's write the method to calculate the result. First, we call a second method to calculate. We only change the status if this is the first call or the result changes. If so, we change the status of port C and pass the result over the connection. This is the method for calculating the result. Here the truth table is simply implemented. Now we add the component class. Here we first add the method that searches for a port. This is determined by the name of the material. This method determines the minimum and maximum coordinates of the material. We first define the maximum and minimum limits. Now we go through all the polygons and check whether they are assigned to the material we are looking for. If so, we go through all the vertices and adjust the minimum and maximum. We give both back. With this method we pass on the results of the ports to the connections accordingly. Now all classes are adjusted and we can test the result. As you can see, our NAND's behavior corresponds to the truth table. This ends the first chapter. The next video begins the development of further circuits, starting with the simple ones and working towards more complex ones.